all, and this is my week one project presentation for CE570 Advanced Structural Mechanics. This is the MATLAB introduction. First, we start with the programming of the body. I ended up citing a code. So we have the definition of the radius, the height, and angle of rotation at the top, and also the number of divisions for each of those different parameters. We move on to the parameterization function. And as you can see, the radius is going to increase linearly as we increase the height. And then as we move in a circle, we have cosine and sine functions taking care of that. And as we can see, we obviously move up in height. The body.grid variable ends up housing all the different values of radius, theta, and the height. That ends up plotting those points in a grid for the cone. Moving on, we have this body.surface variable, and that ends up defining the two different surfaces for the cone, which are the first surface and the bottom base. Note that the radius does not vary, and that's because in the second picture you can see that body.surf function is embedded into the body.para function, which allows for the body.para function to take care of the variation radius through the equations that were covered above. The bottom base is fairly simple, but it's important to note that we step to R base full step because it's much more efficient for our code. We could do R base divided by NR, but it's more efficient to just do it in one full step. It's the same thing. The only curve that we have for our cone is the base circle, and it's just circle at Z equals 0, rotation through the full theta, the same radius. Moving on, we call the plot parameterization function to show the body of our cone, as you can see here. After plotting the body of the cone, we have the definition of the curve at the surface. This curve is a swirl around the cone that's split into 20 different segments. We take it in steps of 1/20. And so the radius decreases as C increases, and then also as C increases, the angle of rotation increases, which allows the cosine and sine functions to move us in a circle. Also, as C increases, the Z value as we move up to the top of the cone. The surface is defined in 10 different segments for S and T. S is related to the vertical incrementing of the surface, whereas T is related to the horizontal incrementing as we move around the cone. As S increases, we move up in height up to 1/5 the height of the cone. And then also as S increases, we decrease the radius to 4/5 of the original radius of the cone. For the angle, we ended up starting at pi. That way we're not obstructing the curve. We're at a different starting point of 0. And then rotate through an angle of 2π/3 surface. Shown below are the for loops of the curve and surface and their displays. S is the first for loop, and the T is the second for loop. So that says that as we start on the first layer, we move around in our different surface segments, and then we move up to our second layer, and then move around again, so on and so forth. Note that there are 5 different components in these vectors, and that is because we have to move the surfaces from 1 to 2 to 2 to 3 to 3 to 4 and 4 to 5. So it's easier to define it as 5 different points that way instead of figuring out something away. On this slide, you can see the swirling display of our curve. Also, the beginning of our surface, as I was mentioning before, with the first layer, we start at S equals 1, around full T equals 10, and then we move up to S equals 2, and then we move around to T equals 10 once again, and so on and so forth. And then our final result is seen top right up here with the curve and the surface shown. Length of the curve and area of the surface are also calculated as. Lastly, we look into the verification of curve length and surface area calculations that were done within the code. Here you can see the parameterization of the curve and the surface along with their limits. To the side, there are the equations for parametric curves and parametric surfaces, and the calculus equations for the length and the area that relate cross products for magnitudes and norms. It's important to note that these integrals for this cone were extremely complex, so I ended up using an online calculator to obtain the values to get final actual length of 6x2 with an area of 17.5317